We're really close to the finish of this semester and this course. We've just got a couple more sections to do, and today we're looking at standard normal distributions. Standard normal distributions are not the only type of distribution, but possibly the most frequently used in statistics. Well, when we talked about the law of large numbers, we talked about that the more trials that happen, the more something approaches the probability of just how many options are out there versus the others. So we know that when you roll a die, you only have, a 1 out of 6 chance of rolling a 2. And when you roll a die, you could roll it 6 times and not get a 2. But if you roll it enough times, then it comes out to be about 1/6 of the time that you will roll a 2. And so that's the approaching. And so what happens here is that if we sample 100 people, 100 men, this is what a histogram would look like. If you increase the sample size, then you're going to have more categories. And then again, we did another increase. If we continue to increase, we would just get smaller and smaller rectangles, and the edges would start to get smoother and smoother. So while doing this would not actually give us a perfectly smooth curve, because we'd always have some little rectangles, this is the graph that we're approaching. And this graph is a normal curve. It's symmetrical on both sides. It is tallest in the middle. This is our normal distribution. So what makes it a standard normal distribution? Well, first of all, a normal distribution is going to be symmetrical, and it's going to kind of have what we call a bell shape. Now, that just means that it's going to be tallest right here in the middle. The edges are the same length. The tails is actually what we call that. But all of these are normal distributions. And in all of them that are perfectly symmetrical with this highest point in the middle, the highest point represents the mean. But as it turns out, the mean, median, and mode are all the same in normal distributions. I have a little note down here, since normal distributions are not all the same, there's a method for standardizing the information so that you can compare them. That is what brings us to that standard normal distribution. On a standard normal distribution, we use what we call and it's up here in the left, 68, 95, 99.7 rule. And you see these numbers right here, 68, 95, and 99.7. And this tells us the approximate percentage of data that falls 1, 2, and 3 standard deviations from the mean. So notice 68 goes 1 below and 1 above. The 95 goes 2 of these marks below and 2 of the marks above. And each mark indicates the distance of a standard deviation. So if you go 3 standard deviations above and 3 standard deviations below, you've captured almost all of the data. We can actually take this information and you could put particular percentages here, because if this is 68 and it's symmetric, then over here, this has to be 34. So that would be approximately 34%. Likewise, right here, this one has to be about 34%. If 95 goes from here at -2 to over here to 2, and I take this 68 out of the middle, I can say, well, 95% minus the 68% in the middle will give me 27% for the total in the blue region right here. And I can divide that by 2 and find out that each of these blue regions then has approximately 13.5%. Now I'm not writing my percentage things on there. I probably should, but these are percentages and I'm just kind of separating them out. So now if I do 13.5 plus 34 plus 34 plus 13.5, I've accounted for 95%. Well, in the same way, we can say, all right, if I go out from the -3 to the 3, I'll have 99.7%. But I can take that 95% out of the middle, and that gives me 4.7% for the total in this little light color section. But since I have that 4.7%, I do need to split it between each one of those. So I'm going to divide by 2, and I find that each one of these light areas is approximately 2.35%. So now from -3 to 3 standard deviations, I have 99.7% of the data. Well, where's the rest of it? It's in these tiny little tails out here, and we're not saying it stops at this point. What happens is we don't know how far out they go, we just know it's past 3. So if we had 100% of the data, we subtracted out that 99.7% we've accounted for. That gives me 0.3% in the little tails. If I divide that by 2, then out in each tail, I have 0.15%, and that is a very, very tiny amount. Because you've got to remember, since it is a percentage, then we're really looking at a 0.0015 probability that anything is past 3 standard deviations from the mean. So you can refigure this out each time if you needed to, but what we basically do then is just kind of memorize these numbers. And I have had students that just try to memorize all the way across because, you know, it's going to be reflective: 34, 13.5, 2.35, and 0.15. And that is the percentage that falls within this area as you're looking at the number of standard deviations from the mean. So this is how it's going to apply. Here's an example problem. Male adult heights in North America are approximately normally distributed, and that's those heights that we were looking at on the first slide. The mean is 70 inches and the standard deviation is 4. Okay, so if the mean, which is 0 standard deviations, is 70 inches, and each one of these distances, every time I go out that far, I've gone 4. That means right here I'm at 74. Over here I was at 66, and you could just label the lines. Now we didn't really need to label all of the lines, but there's nothing that's stopping us. If you wanted to, you could see, so I can label all these different heights over here. And what happens is when it says find the height that is 2 standard deviations above the mean, actually now that I've labeled them, I can just go over 1, 2. And the answer to that one is 78 inches. 3 standard deviations below the mean, that's this answer. So it's 58 inches. Now, if you don't want to label them all, there is certainly a formula, because if you need to get a height, which we would call a particular value, and this is the mean, and this is our standard deviation. This is z-scores over here. The z-score is found by taking a value minus the mean and dividing it by the standard deviation. Or in terms of the entire population, that would be a value from the population minus the mean of the population over the standard deviation of the population. So these are really the same two things. It's just this one is for a sample and this one's for a population. Okay, well, if you wanted the x, a little bit of algebra manipulation means I need to get x by itself. So I'm going to take z and multiply it by sigma. So that would, and z times sigma would equal x minus the mean. But if I add the mean, I can get my x value. Same thing over here if you had a sample. If you can make a note of or look at these formulas, then you can say, okay, so if I needed to go 2 standard deviations above the mean, and my mean was 70, 2 times 4 is 8, plus 70 is 78. Or we could say 3 standard deviations below the mean. That means the z-score is -3. The other part stays the same. So -3 times 4 is -12, and -12 plus 70 is 58. So some people really just like to label and figure it out this way, and some people like the formula. They're both going to work, but it would probably be easiest to rely on the formula if they don't give you a nice whole number. Like if they said 2.25 standard deviations above the mean, well, then it's probably easier to use the formula. So make yourself a note then in words or in this symbols that the z-score, or the number of standard deviations times the size of the standard deviations plus the mean, gives you a particular value. So we can also find percentages that fall within that given range, and this relates to what I was doing earlier. Again, I'm going to relabel things. It's not the only way to do it, but I think it can help you see it. So now, if I want to know the percentage of men whose heights fall between 62 and 78, I can go over here and say, well, 62, I meant to get my highlighter there. 62 starts here, 78 goes all the way to right here, and you can, again, those are labeled underneath. So between that, that's 95%. What about between 70 and 78? Okay, well, 70 to 78 covers this section. But notice I can just add 34 plus 13.5, and that's going to be 47.5. Above 74 goes all the way out. So I need 13.5 plus 2.35 plus 0.15. So I'm going to say 13.5 plus 2.35 plus 0.15. So that's a total of 16% that's beyond the 74 inches. Now what above 82 inches? Well, again, 82 inches is just from this point to the right, and I already have that one labeled at 0.15, and that 0.15 is a percentage. So see, labeling it once, particularly if you have multiple problems to work, just labeling those numbers out there makes it where you can just kind of add and go. I mentioned this on that earlier slide. This is actually the formula to find out how many standard deviations above or below the mean you are. So the z-score is equal to the data item minus the mean divided by the standard deviation. So if we were looking at that in terms of a population, we could say this is z is equal to the particular value minus the mean divided by sigma. Now, if you were looking at a sample, they would replace this with x bar, and this would be s. Everything that is above the mean has a positive z-score then, and everything below the mean has a negative z-score. And if you are right there on the mean, you have not moved at all, so the distance away is 0, so the mean has a z-score of 0. What this does is lets us take these different standard normal curves that maybe have higher hills or lower hills and are spread out a little bit more, and compare them with standard deviations, or how many deviations they are above or below the mean. So here's an example. If we have SAT scores, which the SAT, I'm just going to kind of make a note down here. On the SAT, the mean is 500. It's just how they do the scores. The standard deviation is 100. On the ACT, the mean is 18. They're scored very differently. The range of scores you can get is very different. So this is why we need this to really compare, because these numbers are so different. It sounds like 500 is way above 18, but actually those are both just the mean. So you're hitting right in the middle of that curve. The ACT has a standard deviation of 6. Both tests measure the same kind of ability, and they both have scores that are normally distributed. Since they are normally distributed, then we can make the comparison to the standard normal. So if you score 550 on the SAT, now that's a particular score, so that's my X value. And then you turn around and take the ACT and you score 24. On which test did you really have the better score? It's hard to just see it in this form, but what we're going to do is find z-scores for both of them, and the one with the highest z-score means it's further out there ahead of everybody else. That's the one we want to do. So again, that z-score can be found by taking the value minus the mean and dividing it by the standard deviation. So we want 550 minus 500 divided by 100, and that's going to give me the z-score for the SAT. Well, I don't really need a calculator to do this one, because 550 minus 500 is 50, and 50 over 100 is 1/2. So this is half a standard deviation above the mean. Now let's just back up for a moment and just kind of look at that. I'm not worried about the numbers underneath, but that just means it would put you right in the middle of this pink area. You did better than more than half the people, but you know, there's still a good number up at that end. Let's look at the ACT. Same sort of thing. The z-score on the ACT can be found by taking your score minus the mean divided by the standard deviation. Now 24 minus 18 is 6, and 6 divided by 6 is 1. So this one brings you a full standard deviation above the mean. So in terms of that, if this were the mean and this were one standard deviation, you're looking at a performance right here versus a performance right here. So the ACT is actually the better score. Okay, now we can work this backwards again, find values from z-scores. So if my formula, and I'm just going to back up to the early part where I wrote that on there. Where is it? No, it did. Right here, if we want to get a value, then it's the algebra rearrangement of it. We're going to take the z-score times the standard deviation plus the mean. So z-score times standard deviation plus the mean will give me a particular value. Here we have an intelligence test that has a mean of 100, and I'm missing the word standard deviation, but it's a standard deviation of 16. This is my z-score, and the question is, what is my x value? So my x value will equal my z-score times standard deviation plus the mean. Negative 1.5. Now you can hit times, you can type it in exactly like I wrote it. It doesn't matter. So times 16 plus 100. And that gives me 76. This particular IQ was 76. It's a very, very, very skinny 7 it needs to eat. Okay, Mensa is a group of people with high IQs. Mensa is a real group whose members have a Z-score for their IQ of 2.05 or greater on the intelligence test. So what would your IQ have to be to get into Mensa? Well, here we have a Z-score of 2.05 we have to make. So we're going to calculate what that X value is. We're going to take 2.05 times the standard deviation plus the mean. And that gives me 132.8. This seems like an acceptable answer to me, but I don't think on the IQ test you get decimals. So this one is going to be 133, because if you actually scored 132, you would not have met the threshold of this or greater. So you're going to need to get 133 on that. Now, a different type of problem you have in this section is determining a margin of error. So if you get a statistic from a sample size, there is a 95% probability that it lies within, and we have a little formula here, 1 over the square root of n times 100, and then stick a percent sign after it, of the true population percent. And when we say within, it could be above or below. So when you do plus or minus to indicate above or below, then that gives us the margin of error. And we could abbreviate that ME. So here we actually have then the results of a survey of 1,000 adults. And they were given this list of activity and asked, what do they dread? So this does not need to add up to 100% because a particular adult could certainly dread more than one of these activities. But these were the percentages that were given. So it does say that 46% of those questions said they dread public speaking. That's that very first line. First of all, on part A, we didn't need to particularly focus in on that line because it just says determine the margin of error for the survey. And the margin of error would be the same no matter which category we're looking at. We have a formula for that margin of error. And so we would go and say, well, I know that it is 1 over the square root of n times 100, and we're going to put plus or minus with it. And we're going to say then that the margin of error is plus or minus 1 over the square root of, now this is where we look at how many people did they say that they asked, and it was at 1,000 adults. It's down here beneath it as well as up in the problem. So that's going to be the square root of 1,000 times 100, and then we're going to stick a percent behind it. You can't put plus or minus at once in the calculator, but the parentheses part I have, I'm going to hit alpha y equals enter so that I can do 1 over, then second x squared gives me the square root of 1,000. That's the number of people in the survey. Then I need to hit times 100. So that is approximately 3.16%. It didn't tell me exactly how far I needed to go, so I'm going to say 3.2%. So this one is approximately then plus or minus 3.2%. So that's our margin of error. Now write a statement about the percentage of adults in the U.S. population who dread public speaking. I'm not going to try to write a sentence here, so we're going to talk a statement. Okay, but this is what like a homework question might say. Again, if we're talking about how this applies to the U.S. population, then what we're saying is that it is within that percentage of the true population. So the true U.S. population is within 3.2% of the 46. Well, that's a really awkward way to say it. So what we really want to do, and I am going to write this down, is we're going to do the 46% that came from our survey, and then we will add and subtract 3.2. I'm going to put an arrow here because it's not really equals. It's like, what information does this give me? 46 minus 3.2 is 42.8. And 46 plus 3.2 is 49.2. You know, always make sure on your homework you round it to whatever your instructions tell you to. But what my real statement would be is that there's a 95% probability that the true percentage of adults who dread public speaking lies between 42.8% and 49.2%. So I'm going to highlight what I really focused on. There's a 95% probability that the percentage, now I'm going down here, of adults in the U.S. who dread public speaking is between 42.8% and 49.2%. And that would be my statement. All right, this is the same kind of a problem. So I've just got that formula down there really small. How many books do you typically read in a year? The results of this poll are shown in the figure. Find the margin of error. So here's our formula for the margin of error. So I need to know how many adults they surveyed to find N. And it doesn't say it up here in the problem, but when you look underneath, it says 2,513. So 2,513 is the N value. I'm going to go on my calculator and go 1 over the square root of 2,513 times 100. Now, this one actually does tell me to round to the nearest tenth of a percent. So this is the percentage. So one spot after the decimal would be the tenth of the percent. So that's actually going to make this round to 2.0. So it's going to be plus or minus 2.0%. That's my margin of error. Now write a statement about the percentage of U.S. adults who read more than 10 books a year. So I'm going to write part of this. I'm not going to write all the words. It's just so many. We're going to say that about 95% probability that the actual percentage falls between or lies between, however you want to say that. And now what we're going to do is add and subtract 2% to the number that was given. So this was more than 10 books a year, so I'm looking at this last column, which is 36. If I subtract 2 from that, I'm going to say 34%. And if I add 2%, it's going to be 38%. So the 95% probability that the actual percentage of U.S. adults who read more than 10 books a year falls between 34 and 38%. And I am definitely in that group. I think I've read 2 books this week. So anyway, you just have to have this little formula. It's certainly not hard to do. And just that multiplying it by 100 is why you can just write the percentage at the end. So don't multiply by 100 and then try to move a decimal. That 100 is already moving the decimal for you. So some closing notes. Margin of errors are often actually higher than calculated when you deal with surveys, because there are other things that go into surveys. And if you take statistics class, you would learn a lot more about that. But not all surveys are created with very good questions. Sometimes people lie when they give answers. They just think one answer is going to sound better than another. So a calculated margin of error is actually very conservative. It's probably, the real margin of error is probably bigger than that. Now, not all data can be approximated by the normal distribution. So we know that not everything falls on a normal distribution, and statistics does use other distributions, but we use the normal one the most. And many things, like we talked about the law of large numbers, if you involve enough people in the study, then it will approach a normal distribution. All statistical analyses do have a margin of error. So we know that when we're doing statistics, our results are not perfect. Actual results may not at all be the same. So the last thing I'm going to say here is just give you a last glance at the formulas. And I think our very first formula might have been, this is one of the things that you will want to know is 68, 95, and 99.7. And you don't have to memorize this part, but I hope you understood how I got that, because that's going to help you work some problems. So the 68, 95, and 99.7. This is really poor writing, but this is the formula for how to find the z-score, and then this is rearranged for how to find a particular value, and we do need to use those. And then the other little formula we used is right here with margin of error, how to calculate the margin of error. All right? We've got one more lesson after this one. You guys are almost done. Hang in there. Send me any Ask the Instructor questions you have.